In business, making decisions based on a gut feeling is gambling with your profit margins. When a manager claims that a new working method is faster or that a machine change has reduced errors, a Lean Six Sigma black belt asks one cold, hard question. Can you prove that statistically, or was it just pure luck? This is where we enter the world of hypothesis testing. By understanding the battle between the null hypothesis, H0, and the alternative hypothesis, HA, and by mastering the ultimate rule of the p-value, you will never make a blind operational decision again.
Welcome to The Explainer. Today, we're taking those abstract, sometimes intimidating statistical concepts and turning them into absolutely foolproof decision-making tools for managers. We're going to adopt the mindset of a Lean Six Sigma black belt. Now, this isn't just about crunching numbers or doing math, it's about operational excellence. It's about looking at a so-called improvement and having the rigorous framework to definitively prove whether it's a genuine, bankable breakthrough or just a random fluctuation in your data. So let's kick things off by looking at the anatomy of a hypothesis test, which is essentially the battle of the status quo versus the challenger.
Every single statistical test is, at its core, a boardroom battle between two competing statements. First up, we have the null hypothesis, represented as H0. You can think of this as the status quo. It's your baseline assumption that absolutely nothing has changed. There's no effect, there's no difference, no improvement. It's basically the statement that says, hey, that highly expensive new method, it's exactly the same as the old one. Standing right against it, we have the alternative hypothesis, or HA. This is the challenger. This is the bold statement you actually want to prove. It claims, no, wait, the new method is significantly faster. Your job as a decision maker is to find enough hard evidence to knock out the null hypothesis.
Now, this dynamic directly maps out our executive risk. When you make a call, you can make two distinct types of errors. A type 1 error, also known as an alpha risk or a false positive, is an absolute nightmare. This means you reject the status quo when it was actually true. In the real world, this means you implement a massively costly change because you genuinely think it works, but reality says the improvement you saw was just a total fluke. On the flip side, we have the type 2 error, the beta risk, or the false negative. This happens when you fail to reject the status quo, even though the challenger was actually better. In practice, you miss out on a massive optimization simply because your data sample was too small to statistically prove the effect. Both are risky, sure, but type 1 errors are what actively drain capital.
That brings us to the golden rule. To avoid these errors, we need an ultimate judge, and that is the p-value. We rely on this concept all the time. The p-value is the absolute ultimate judge in inductive statistics. Put simply, it's the probability that the observed difference you're looking at happened by pure chance. It tells you the exact likelihood that your data is just random noise rather than a true underlying change in your process. So the crucial question you have to ask yourself is, what level of risk are we willing to accept? Well, in Lean Six Sigma and general scientific practice, we establish a standard significance level, known as alpha, at 0.05. That's 5%. We are stating, for the record, that we only accept a 5% margin of error for our boardroom decisions. If the chance that our results are just a random fluke is greater than 5%, we do not act. We demand 95% confidence before we even think about spending the company's money. And this brings us to a brilliantly simple, absolute classic memory aid used by students and executives alike. Say it with me. If the p-value is low, meaning p is less than 0.05, H0 must go. If p is low, we kick the status quo right out the door, we reject the null hypothesis, and we embrace the alternative hypothesis. We've statistically proven our case. Conversely, if p is high, meaning 0.05 or greater, H0 must stay. We failed to prove our case, and the status quo remains intact. All right, let's put this into practice. We're going to dive into a real-world case with BlueprintRM&Co.'s premium e-commerce logistics division. Let's set the stage here. Our black belt is evaluating operations, and there's a glaring problem. Returns of luxury items are just taking way too long to process. A vendor comes in and pitches this highly expensive, brand-new automated scanning software designed to speed up the registration of these returns. Now, a traditional manager might just watch the demo, see it go fast, and sign the check. But our black belt? They demand a rigorous test to protect the bottom line. So we formulate the hypotheses live to set up our test. Our null hypothesis, H0, assumes that the processing time with the new software is exactly equal to the processing time with the old software. That's the status quo. Our alternative hypothesis, HA, states that the processing time with the new software is strictly less than the old software. That is the challenger statement we are trying to definitively prove to justify this heavy investment.
Okay, the black boat runs the test. Let's look at scenario A. The average time for the new software actually looks a little bit lower to the naked eye. The vendor is probably cheering right now. But we run the statistical analysis and it spits out a p-value of 0.42.
So what does a p-value of 0.42 actually mean for the business? It means there is a massive 42% chance that this observed difference is just random noise. A 42% chance it's a complete fluke. Because p is high, h0 must stay. We absolutely cannot reject the null hypothesis. The Black Belt's recommendation to the board is clear. Do not buy the software. Investing now would be committing a catastrophic type 1 error, wasting valuable capital on a phantom improvement. But we don't just stop there. Lean Six Sigma is all about continuous improvement. The team goes back to the drawing board, optimizes the software integration, refines the internal process, and we run scenario B. We test it again. This time, the decrease in processing time is much sharper, much clearer, and our rigorous statistical test yields a brand new p-value of 0.012. Let's apply our golden rule here. A p-value of 0.012 means there is only a 1.2% chance this result is a fluke. We are well below our strict 5% threshold. If p is low, h0 must go. We officially reject the status quo. We have statistically, undeniably proven that the new software is genuinely faster. The executive decision is now foolproof. We roll out the software confidently across the entire logistics floor. To wrap things up, let's talk about the strategic value of all this, the boardroom bottom line. So why does all this matter to you as a focused learner and a leader? It's simple. Hypothesis testing and the p-value rule protect your organization from wasting capital on imaginary improvements. It ensures that true, data-driven breakthrough changes are actually captured and scaled. By forcing yourself to clearly define the null and alternative hypotheses before making a move, you systematically replace dangerous gut feelings with foolproof statistical logic. You literally elevate the entire operational standard of your company. So the very next time someone pitches you a massive operational optimization, ask yourself, what is the p-value? And are we truly beating the status quo or just getting lucky? For education and entertainment,